Every prediction starts with a simple question. Can a machine learn from data? Can it look at thousands of houses and figure out how much a new one should cost? Can it discover patterns without anyone explicitly programming the rules? Today, the answer seems obvious. But the ideas that made this possible became the foundation of modern machine learning. The story begins with a simple question. Suppose you want to predict the price of a house. How would you do it? One option is to manually write rules. But what if there are thousands of houses? Different sizes, different numbers of bedrooms, different prices. Writing rules for every situation quickly becomes impossible. So instead, we let the machine learn from examples. This is called supervised learning. We give the algorithm inputs and the correct outputs. Then it learns the relationship between them. Imagine collecting data about houses. For each house, you know its size and its price. After looking at enough examples, a pattern starts to appear. Bigger houses usually cost more. The goal of the learning algorithm is to discover that pattern automatically. And one of the simplest ways to do that is linear regression. Linear regression tries to fit a straight line through the data. Once that line is found, the model can estimate the price of a new house it has never seen before. But this creates a new problem. How do we know if our line is good? Researchers solve this using something called a cost function. Think of the cost function as a score. If the model's predictions are far from the true prices, the score becomes large. If the predictions are close, the score becomes small. So the goal is simple. Find the line that produces the smallest possible error. But how do we find that line? That's where gradient descent comes in. Imagine standing on a mountain in thick fog. Your goal is to reach the lowest point. You can't see the entire landscape, but you can look around and take a small step downhill. Then another, and another. Eventually, you reach the bottom. Gradient descent works the same way. It starts with a random guess, measures the error, then repeatedly adjusts the model parameters in the direction that reduces the error. Step by step, the model improves, and eventually finds the best solution. But when datasets become very large, another challenge appears. Speed. One approach, called batch gradient descent, looks at the entire dataset before making an update. This works well for smaller datasets. But with millions of examples, it becomes slow. So researchers developed stochastic gradient descent. Instead of looking at every example at once, it updates the model using one example at a time. The path becomes noisier, but the learning process becomes much faster. And that's why stochastic gradient descent became one of the most important optimization techniques in machine learning. So the journey is surprisingly simple. Start with data. Define a model. Measure the error. And repeatedly improve the model until the error becomes as small as possible. That's the foundation of linear regression. And it's also the foundation of many machine learning systems that came after it. But there's one problem. What if a straight line isn't the best fit for the data? And what if the goal isn't to predict a number at all? What if we want to predict whether something belongs to one category or another? To answer those questions, researchers developed more powerful techniques: locally weighted regression and logistic regression. And that's exactly what we'll explore in the next video.